Welcome to the Explainer. So I want you to imagine, just for a second, that the unimaginable has actually happened. The cities are completely silent, the roads are totally empty, the power grid is finally starting to fail. In this post-apocalyptic world, humanity has been pushed to the absolute brink, and the truly daunting task of rebuilding our entire species falls squarely on the shoulders of whatever survivors are left. It's a fascinating and, let's be honest, kind of a terrifying premise, right? But exactly how many survivors do we actually need to pull this whole thing off? Okay, let's dive into this and look at the very first major hurdle we'd face.
It's the classic trope, right? You've got one fertile man, one fertile woman, some quiet corner of the post-apocalyptic world, and basically the entire future of Homo sapiens becomes their personal group project. But if we're asking whether literally just two people can restart humanity, the answer is, well, technically yes, but they would also be creating what is arguably the worst family reunion in human history. Here is exactly what happens to our genetics in that scenario. With only two founders, the sons and daughters are only working with the genetic variants present in those exact two parents. So by the time we hit the second generation, literally every possible partner is a sibling. The family tree basically stops looking like a branching tree and becomes this tightly woven wreath. Their children would have no choice but to reproduce with siblings, cousins, or eventually their own descendants. So the crucial point is this concept right here, inbreeding depression. Look, every single person carries harmful genetic variants, but most of the time they cause absolutely no problem whatsoever because they're recessive. You basically need a harmful version of the exact same gene from both parents for it to actually show up. And unrelated people are highly unlikely to carry the exact same rare variant. But siblings, they're getting their genes from the exact same two parents. When relatives have children, those matching stretches of DNA meet up, and all those hidden recessive variants suddenly introduce themselves. To really understand just how impactful this is, we don't even have to look at hypothetical sci-fi scenarios. We can just look at real history. Back in the 18th century, this absolutely devastating typhoon hit the Pingalap Atoll in Micronesia. The disaster reduced the entire population of the island to roughly 20 survivors. Just 20 people, that's it. Now, the community did eventually recover its numbers, but here's the catch. One of those 20 original survivors just happened to carry a rare recessive variant for a condition called achromatopsia. It causes severe color vision loss and extreme light sensitivity. In a massive, globally mixed population, a variant like that stays super rare. But in this tiny founder group, it multiplied. It eventually affected roughly 1 in 10 people on the atoll. This perfectly illustrates a really vital rule. Population growth copies the surviving genetic library, but it does absolutely nothing to restore the books that already burned. Because ultimately, as the saying goes, genetics is probability, not divine punishment. It's basically a roll of the dice in a Punnett square. Not every single child of related parents is going to be sick. But across generations, those risks accumulate incredibly fast. Starting a population with just 2 people isn't a 100% biological guarantee of extinction, but it is basically holding a terrifying chromosome lottery ticket. Let's move to and see how this builds. Section 1, the demographic hurdle, moving from hundreds to thousands. Because even if we somehow escape that severe genetic bottleneck of just 2 people, passing the 10 or 50-person mark introduces an entirely new threat, which is demographic randomness. To really wrap our heads around this, we have to distinguish between the census population size, so your total head count, and what actually matters, the effective population size. You see, humans aren't just breeding marbles you can blindly pull out of a bag. Some people are infertile, some, unfortunately, die young, and some simply choose not to have kids, which is completely fair. Just look at how this data breaks down in a real survival scenario. If your census headcount is exactly 100 people, the actual breakdown might look something like this. You've got 40 children, 20 older adults, maybe 10 who are injured or sick, leaving a slice of only 30 people of reproductive age. If there's an uneven ratio of men to women in that group of 30, or if just a few succumb to illness, your effective breeding population suddenly shrinks down to just a tiny handful of people. Biologists actually used to have this rule of thumb called the 5,500 rule for conservation, but modern research has updated this significantly. The new targets are closer to 100 effective breeders just to limit dangerous inbreeding in the short term, and 1,000 effective breeders to actually retain evolutionary potential for the long term. And remember, that means your actual survivor headcount, the census size, needs to be way, way higher than 1,000 to actually yield 1,000 effective breeders. If you don't hit those numbers, you risk falling into what conservation biologists call the extinction vortex. Let's walk through this downward spiral. First, a population shrinks. Then, inbreeding and that loss of genetic diversity start reducing the overall health of the group. Well, that lower health means infant mortality goes up and population growth drops. So the population becomes even smaller, making the inbreeding and those random losses hit even harder. It's a cycle where bad luck literally becomes your doom.
So, you might be wondering, how do we cheat the system? What if a small group of survivors stumbled upon a fully stocked, perfectly preserved cryobank full of frozen embryos from thousands of totally diverse donors? I mean, it sounds like the perfect technological workaround to instantly boost our effective population size, right? Well, there's a massive, massive catch. Maintaining sterile procedures, managing all that liquid nitrogen, and keeping those embryos viable requires a massive, perfectly stable power grid.
And hey, even if you miraculously have the electricity, you still have to raise them. Which brings us to a harsh but honestly very funny truth. Babies are, strategically speaking, terrible employees. In a brutal survival scenario, a baby consumes your precious food, constantly interrupts your sleep, demands around 15 years of intensive care and education, and absolutely cannot help you repair a broken diesel generator. Population growth is inherently going to be delayed.
Section 2. Rebuilding a Civilization. Why Humans Are an Ecosystem. Now, what's really interesting about this slide is how it forces us to expand our scope. Surviving biologically is one thing, but to maintain an actual functioning society, we have to consider this incredibly witty quote. Redundancy sounds inefficient until the only dentist falls off a roof. When we talk about minimum populations, we usually just fixate on genes. But if you only have one single person who knows how to purify water, or one person who knows how to safely deliver a baby, a single minor accident can suddenly cripple your entire settlement. Think about the basic redundancies we'd need: obstetrics, electrical engineering, water sanitation, agriculture. Modern civilization isn't just downloaded into one brilliant human brain, it is highly distributed across millions of specialists and enormous, complex supply chains. A surgeon literally can't operate without anesthetics. Those require a factory, which requires a power grid. You can only scavenge canned food and antibiotics for a few years before you are completely forced to recreate these essential skills from scratch. And repopulating the Earth takes an immense amount of time. Look at this timeline. Even if we start with 1,000 perfectly healthy survivors and assume a super clean mathematical 2% growth rate per year, it still takes about 3.5 centuries just to reach 1 million people. It would take roughly 800 years to return to our current 8 billion. But in reality, famine, conflict, disease, and totally unpredictable disasters would constantly push back against that growth, making the timeline incredibly slow and fragile. Which brings us to this brilliant analogy to sum things up. A lifeboat may technically hold 20 people. That does not make 19 passengers and one sandwich a sensible strategy. When we ask what the smallest human population needed to repopulate the Earth is, we really shouldn't be asking for the absolute biological minimum. We should be asking for the responsible minimum. And this brilliantly illustrates the whole journey we've been on. Rebuilding Earth is truly a ladder of risk. At the absolute bottom rung, 2 survivors guarantee a genetic catastrophe. Scale up to a few dozen, and you're just playing demographic roulette with severe inbreeding. Hit 100 to 1,000 effective breeders, and you finally get a biological buffer. But to achieve a durable, flexible civilization, one that doesn't completely collapse the moment an electrician breaks a leg, you need tens of thousands of skilled, diverse people. So, I want to leave you with this final, provocative thought. If disaster strikes, are we just trying to save human bodies, or are we actually trying to carry an entire ecosystem through a keyhole? True repopulation isn't just about creating as many babies as possible. It's about bringing our shared culture, our intricate skills, our diversity, and our mutual trust into the future. It's about building a population capable of creating the next population without losing everything that makes us human along the way. Thank you so much for joining me on this explainer, and I really hope this changes the way you look at the complex, interconnected web of human survival.